So everything sounds really loud here. So please give me feedback if I'm shouting in your ear. And also, please whistle if I go too close to that thing. Because I'm told I can't stand over there to block the slide. So I might not realize I tend to walk around a bit. So a few words before we go into search, a few words of where I'm coming from. I work for a company called Reactor, also Reactor Ventures, which is our seed investing arm. We do all kinds of consulting from business to design and technology. You see some of our clients over there. We worked on in-flight entertainment. That's Finnair's new system. Amazingly, they're running Node.js. So expect to see movies like nodes in the plane and things like that when they run out of Silicon Valley ideas. We've done apps. These are also for Finnair. iOS, Android, also Windows Phone. So we're not really specialized in anything, you could say. Also, I'm not specialized in anything. I worked on all kinds of technologies. Some of our colleagues are working on really weird stuff like this, like full wall-sized touch screens, all kinds of cool stuff. That's from NASDAQ. We're not listed, but I've been there for that reason. So that's Reactor. That's where I work with 300 other people, 350 other people. Recently, I've been working on mostly mobile apps. So for the past 2 years, I've worked on Android, iOS, and Windows Phone apps. Yes, some people still do have Windows phones. I don't particularly like Windows Phone, but we had this sort of habit that we try to get a single team together that builds all of the apps with the same group of people. So everyone has their own backgrounds and so forth, and we try to find matches that that are sort of cross-functional enough that the whole team can do everything. So the way I got to this, the topic of search, kind of started with this project we did for the sort of Finnish major television broadcasters. So there's the public broadcasting company, and then there's two sort of commercial companies, and the three of them basically own 100% of the market. So they all have their own online streaming services and their own websites and apps where you can search for content and watch content. They wanted to do kind of like a shared collection of all of their content. So we sort of built a single app that aggregates all of their content. And in that case, search became an interestingly difficult issue because you had 3 search engines, 3 databases, somewhat varying type of content or data quality. And we were supposed to not be biased to any of the 3 parties. So they were paying for it jointly, splitting the bills. And they had all kinds of desires that they want every content provider to have roughly equal amount of content on the screen, but it needs to be relevant to the user. So weird stuff like that. Then there's another app. This is the most recent. I've been working on an audio podcast application, which is also for one of the broadcasting companies. They also own like the major commercial radio stations. So I think they have like 6 stations, and their market is 90% of the audience or something. So they're sort of moving into digital and taking things online, and this sort of making podcasts from radio broadcast shows and producing original content for just online or mobile listening. That's kind of what they're toying with. And here, for example, one of the ideas in the concept was that everything is available offline. So we would download clips or podcasts to your mobile and give you a powerful search to find these episodes. So some of the programs, they put out dozens of clips of different lengths per day. So the content keeps piling up fairly quickly. So that's search. And the reason why I'm standing here is because I found it surprisingly difficult. So my background is I'm a Java dinosaur. I worked on stuff like PHP and Java 15 years ago. And over the years, I got sort of used to search being something you buy off the shelf. You install the latest open source thingy on the server, and everything just works. If you don't like that particular server, you pick a different one. And programming languages aren't an issue because a Linux server can run pretty much anything. But on mobile, it was very different. So on mobile, suddenly I can't run just like Python on an Apple iPhone or Android devices. So the selection was much more limited. Also, there's some constraints on mobile devices that aren't really an issue on the server, like how much storage do you have, how much memory do you have, and so forth. So the title of the talk is Full Text Search. Would anyone want to try and define what that means? What is full text search? Anyone?
I have a microphone, so it's easier for me.
Go ahead.
Could I use like Google in your phone? Example?
Well, that's a fairly easy answer. So there's no official definition for full text search. This is what Wikipedia says. Wikipedia definitions are usually so and so, and this is also fairly general. Like if you read this description, it basically says it's a search. That's how we expect search to work, right? When you say search, you expect it to span all the relevant columns in your database or all the relevant fields in a document and so forth. So that's like the default. So the way I'd like to define full text search for this talk is that it's a good search, something that gives me relevant content, relevant hits when I type in some words, and it ignores my spelling errors or minor differences in like plural, singular form. It basically gives me what I'm looking for, so sorts them so that the odds of me finding what I'm looking for on the first page, that'd be really nice, right? So that's full text search for me, and it basically requires, I think, to win this search game, I think it requires 3 elements that all have to be in place. So there's UI, the way we interface with the ability to search. Then there's the content. We need to understand the content, manage it. And we also need to be able to index it so that we can efficiently, conveniently search it and retrieve information. So we're going to look at these 3 things over the next, 30 minutes. Let's start from the UI. So the definition for full text search that I quoted just now, it all boils down to the user interface. It has nothing about the technical implementation under the hood. Well, that's a technical detail, right? So whatever we do with the UI, we should try to keep in mind that the user gets what they want. It doesn't really matter if your algorithm is more correct than what the users are asking for, because it's the perceived quality that usually matters more. So we're gonna try and serve the user. One of the things, like a crystallized goal, would be to avoid having to scroll or making the user scroll. So any way you can find or think of that gives or increases the odds of what the user is looking for being above the fold or within the first page, preferably visible on the screen. That'd be great. As an example, in the podcast application here shown on the right, what we did was we have three types of content basically. We have broadcast channels, so live radio. There's only a handful of them. Then there's podcasts, and then there's episodes of those podcasts. So when we do a search for some keywords, whatever the user thinks of, we basically search all of these documents, and we return them in a kind of rank order, but we group the results. We group them such that the matching radio channels are on top, even if that match wasn't as strong as something down in the episodes. Similarly, we put the podcast next, and then the episodes last. Can anyone think why would this make sense?
From the perspective of what you said about full text searching, it doesn't make sense because you said that it should be the most important thing should be on the top, and if you group it this way, it's really possible that it will be below the screen right now.
Right. Yeah, it's contradictory. The top item might not be the what the algorithm thought would be the highest score, the strongest match. But what we're trying to do is ensure that what the user is looking for is on the first page. And we found that this is actually a fairly good optimization. So, for example, if you search with the term radio, it matches all of the 6 broadcast radios we have. And if you search for radio, the odds are that you're actually looking for one of those 6. If you weren't, 6 isn't too much to scroll over, so it's not that bad, even if they're not looking for radio. Similarly, for the podcast, just by experimenting with different words that people search for, we could see that it doesn't actually produce too many hits in the podcast category either. So what this actually does is it doesn't necessarily, if you're looking for an episode, it doesn't necessarily give you the episode you're looking for on the first screen. But if you keep on typing and you narrow down the search, you very quickly lose the radios, you very quickly lose the podcasts, and what's left is very quickly what you're looking for. It might not be after 3 or 4 characters, but 5, 6, 7, you're probably there. And it's not a scientific proof. We just observed what our data and our ranking algorithm produces, and does it feel good? So that's what we did. And really, how good your search is kind of like a combination of the tables. Do you know table stakes? Like in poker, in order to even sit on the table, you have to pay something. In search, that's finding matches. So it would be a lousy search if it doesn't even at the very last item in the search results include something that actually matches or should match. The goodness is really how well you rank them, how well you sort the results, so that the really important item is actually on top. So here's a few things that we, as in the tools and sometimes the programmers, apply in doing that. One is the number of occurrences. So you're looking for a term, how many times it appears in a document or a field or a column, tends to raise the score. Length of match versus length of text. Not quite as trivial, but still, if you're looking for radio, it gives you a better score if there's a document called Radio Rock versus a 1,000-word blob of text that includes the word radio once somewhere in the middle. Similarly, starting position, early on, higher rank, later on, lower rank, and so forth. Full word matches, again, on a word level, the relationship between the length of the match and the length of the total word, similar thing. Certain columns might have different weighting. So this is called column weighting, where we define that whatever is found in this title column, it weighs more or gives a bigger score than an equal match on the some other column. More, let's say, difficult things, dates, like the age of a document. It's really difficult, actually. If you think about matching words, we usually do prefix matching. So we start from the beginning of words and see if the word actually matches, or the starting of the word matches what we search for. And there's data structures that are specifically geared for this. You pick up a computer programming 101 or data algorithms 101, and you open the page, whatever, you're bound to find something like trees and so forth, which are very good at this. Dates, not so easy. So most of the search engines that I've found, they either don't support aging, or they don't really document them so that I could understand. It's like black magic if they do it, and it's hard to actually verify if it actually works. If you're doing your own algorithm, that's different. So implementing your own custom ranking function, it's easier. You can apply thresholds, and basically you take a number from another algorithm, and then you apply some kind of a factor based on the date of the document. A similar thing might be popularity amongst users. So again, it's a dynamic property. It's not something that you write once into the index and it stays valid. It's more like a real-time check or a pseudo real-time check. How many times this particular content has been accessed in the last week or last day or last hour and so forth. And finally, we could look at heuristics. We could look at what people actually click on after searching. We could try to find relationships between what they wrote and what they ended up viewing or selecting, somehow indicating that that's interesting, that's relevant content. You could also go into machine learning. Not my field of study, but a lot of people seem interested in that. So a lot of different ways that you can affect the quality of your ranking. So the good news is most of this is done by readily available tools. We'll look at a couple of them. And the remaining things they're a bit difficult. They're not impossible. So that's good. So here's a few guidelines for implementing user interfaces. Should be basics. We'll just run through them. Don't block the UI thread. Also, don't block the database, which is often like serial access, at least for writes. Not all databases support parallel read and write, for example. So having a lot of writes going on might also prevent reads. Even if your tools support that, you might not actually be using that functionality. So you better be careful with that. Also, don't block new searches with old ones. So, for example, if I type faster than the search engine gives me results, I don't want the intermediary steps be sort of queued and executed one at a time. I want the latest, always. Also, if you can, show preliminary results early. So it's a bit like cheating, but sometimes the users like that. Even if it's not correct, it gives me a feeling that something's happening. Even if something's not visibly happening, I'd like to be confirmed that, affirm that something is actually happening under the hood. It's just a bit slow now. This activity indicator, very good. If you make it cute, even better. Also, in terms of user experience, it's sometimes not that intuitive to tell whether the search engine just didn't find anything or if it actually didn't even try. So try to take care of the empty state and distinguish between I haven't searched from I did search but it didn't find anything. And finally, adding terms should narrow results. This is not an absolute truth, but I think that most of the time that's the way it should be. So comparing this to Google, if you type words into Google and Google doesn't find anything, it basically starts dropping words. It starts loosening the matching filter so that it finds at least something. If you're on a mobile phone, the odds are, depending on your application, of course, but I would wager, I guess, that most people here, most of the apps you use, on average, you'd like the results to get narrower and narrower if you keep on typing. So that's a few words about the user interface or the user experience end of the things. Then there's content, but that's content is boring, so let's skip that. And then there's the index. Now, I promise that I'll mention a few tools. There's like specialized search engines available. Back in the server-side Java world, we used Lucene all the time, Apache Lucene. And Lucene was so popular that people started writing ports of Lucene to their environment. So one of these ports that's still more or less alive is called C Lucene. And being C, it's sort of available to on iOS. I'm saying sort of because it's not really meant to be run on iOS. And if you just drag and drop the C Lucene source code into your project, it doesn't quite compile yet. So you need to work on the build a bit. But some people have done that work. One of them is a CocoaPod called BR Full Text Search. It's basically a wrapper over the C Lucene API, which is really low level. BR Full Text Search gives you let's say a fairly narrow interface, but the odds are that it does enough for you. On Android, there's mobile Lucene, similarly a kind of a port of the Lucene proper on Java. So Android doesn't have all of the packages that that the server-side Lucene uses. So they've had to provide alternative implementations and so forth. And basically, they're trying to keep up with the actual Lucene project. I wouldn't expect to be following the major releases very quickly, but the available packages actually work. So I wouldn't care too much if it's not the latest. And then there's SQLite, the true workhorse, available on both platforms. SQLite, since forever, it's had something called FTS tables. So they're basically virtual tables, a bit of custom or a special SQL syntax that you use to populate the index and search the index and so forth. It's also fairly low level, but kind of the environment is fairly familiar for people who've used relational databases. And the odds are that your app has SQLite. It's fairly good anyway. So here's a quick sample what it might look like if you used C Lucene through the wrapper. Here's you need a couple imports. You need to tell the library where to find the index file. You might configure it a bit. I've configured it to use Finnish for stemming or analyzing. So Lucene tries to look at the data it finds and then manipulate the words or extract words from the sentences without punctuation and so forth. And well, we'll mention stemming a bit later, but kind of similar. Depending on the language, you treat it a bit differently. And then when you're ready to add something to the index, you basically create documents, key value maps. This is how BR full text search does it. It has a few special field names, the KBR search field name, title, and value. But in practice, you could use your own names like A, B, and C columns, or column 1, column 2, and so forth. There's synchronous, asynchronous versions of everything, so it's fairly flexible. Now, searching these documents, being a wrapper for C Lucene, you pass in Lucene query strings. This is where it gets nasty. So simple searches like this, fine. But the user is not going to type this in. The user is going to type in surf, board, and other stuff. So it's for the programmers, it's one major challenge is to reliably turn the input into valid Lucene query strings with proper escaping and so forth. If you want to boost certain columns or fields, you can do that at this stage. Lucene actually supports column boosting at the sort of column definition time, but it also supports sort of after the fact boosting by annotating the query strings like that. Hat 10 means something like multiply the score by 10 or something. Fetching results, not that convenient. Basically, what's usually the case with the indexes like Lucene is that you don't get the actual documents back. Sometimes you do, but most tools give you just something and an identifier. And then it's your job to map the identifier back to the actual business objects or the content objects that your code wants back. So there's another step that might, for example, slow you down a bit. So you might want to do this asynchronously. Basically return the IDs very quickly and then let the UI asynchronously fetch them in small batches and display in the UI. Mobile Lucene, the Android version, similar thing. There's, again, wrappers available, not that many, but at least a couple. One of them is called Lucene Study, and it's really it's not usable as is. It's more like you clone that repository and copy, paste, modify a bunch of things. But it basically gives you a harness, a framework that you can take and modify for your own uses. Has a fairly similar interface. Doesn't leak too much of the Lucene internals, which are really low level. That the mobile Lucene itself actually reveals all the nastiness, but the Lucene study wrapper basically hides that. So you have to look at it for a while to modify the framework, but then you're good. SQLite tables or FTS tables. They're basically virtual tables. You can create them with one or more sort of indexed columns. You can specify different kind of tokenizers. ICU is good for languages with weird characters, like non-Western characters, for example. And you can configure a couple other things that I've never even touched. But this is usually good enough. Inserting or adding documents to the index is just an insert. The interesting bit here is the document ID field. So that's the mapping between what you put into the index and being able to map it back to the actual content object that you want in the UI. And then every now and then you might want to optimize the table. It takes a while, so you don't want to do this while the user is actively doing stuff. But you might schedule it for like the app's idle time. It takes a few seconds at least, so don't do this in the middle of navigations or stuff. Searching from documents. At first it seemed like, oh, this was easy. We did this on Android a few months ago. That was my first time I used SQLite FTS tables. And basically I said, well, I just use this match operator in the SQL statement, and then order by this match info function that SQLite provides. The problem is the matches didn't actually make too much, well, the matches made sense, but the sorting didn't. So it almost seemed like it's a random order that things come out in. And the problem was that SQLite is fairly good at this sort of indexing stuff, but ranking, it doesn't do out of the box. So what basically everyone ends up doing is going to GitHub or Stack Overflow and then look for SQLite custom rank function, and then they copy paste the same C code and port it over to their language, Java or Swift or Objective-C usually, and then maybe modify it a bit. So there's a fairly standard ranking function called copy BM25 and a couple of variants of that. And usually people end up taking that as a basis. And when you start using this ranking function, it suddenly the 2 or 3 liner became 11 liner, and suddenly you start remembering why SQL isn't that nice. The keyword join is like a giveaway. So basically, there's a lot of power here. So you are able to implement your own ranking function. SQLite takes care of the indexing storage. It's very good at that. It's fairly fast, but the big differentiator here is how good your ranking function is. We actually did this in pure Java by first parsing the string that we got out of the select statement. Then we realized that, oh, wait, SQLite on Android, it actually supports custom SQL functions. So there's a smarter way to do it. Similarly, iOS, the SQLite wrappers like SQLite Swift, GRDB, FM database, I think, they provide wrappers that make it easier to register custom functions. And again, Stack Overflow, GitHub, you have a fairly good base of ranking functions to start with. So that was UI content and index. We skipped over the content at first. I wanted to sort of leave it last. And that's because there's a one more thing kind of thing here. So even when you're done with the tooling and you've set up your ranking functions and so forth, there's still the challenge that we don't necessarily understand the data well enough yet. So the simple word surfboard actually is 2 words. And if you look closer, you can identify much more potential words. So should we match a document that mentions surfboards if I search for surf? Yes. Board? Yes. It's sort of relevant. But then boa or bore, they're both technically words, dictionary words, but they don't relate to what I'm looking for like if it's part of the word surfboard. So again, it's not the technical existence of the match. We're trying to drop these kinds of matches, the red matches, and only rank the blue matches that actually make sense. And that's one of the challenges. So let's take a look at a couple more examples. Massacre. How many words do you see?
One nasty one.
One nasty one? Well, it depends on nasty. But again, mass, the beginning of the word, yeah, I would consider that a match. It's not actually, it doesn't relate to massacre, but if mass is what you type in, it actually matches the beginning of the word, hence it's a potential relevant document here. Then if you search for ass, the animal, of course, it probably shouldn't match because it's in the middle of the word. It leaves another word, a proper word, acre, but then like a dangling individual character M. It doesn't seem like that's a word boundary, so we probably shouldn't include those in the as a sort of valid match. Slingshot, kind of similar, except that this time it splits into a sling shot or a slings hot. No dangling characters. It actually splits the whole word into two parts in 2 different ways that are all dictionary words. So and this is where it gets difficult because it's really, really hard to tell the computer why it shouldn't consider hot as an indexable term that we should match here. When technically it looks just the same as shot. So putting these things like next to each other, we're doing prefix-based searches because that's how we are able to make the actual information retrieval fast. We're looking at where to start matching. That's the key problem here. So obviously, the beginning of the word is always a potential. It's one position where we should start matching. But then, what about the other blocks? So we can first of all drop the beginnings of the word. These, for example, sling, or mass, or surf, because surfboard matches surf anyway. It's a prefix search. And we can only worry about the different substrings after the first word boundary. So a small optimization there. Then there's, depending on language, if you look at German or Finnish, you can find words with 5 or 6 compound parts to the word. In English, there's not that many. One is craftsmanship, where manship kind of technically exists, at least in an Urban Dictionary, but probably shouldn't match it. But the odds are that your dictionary doesn't contain manship anyway, so it might be a non-problem. But how we split these words, that's one key challenge for the programmer wanting to do a good search. So the way you do it typically is by dictionary. There's a whole bunch of research around how you do this with all kinds of machine learning and stuff, comparing languages, translating between dictionaries and so forth. But in practice, what people do is they look from the beginning and start scanning and matching against the dictionary. Is the beginning a proper word? Is the tail a proper word? If not, is it a compound word? Recursively checking things like this. So you take a word, you move the window, you look for a full match. So this doesn't count. This counts because the head and tail both match, and so forth and so forth. So the problem with the endings is also something you might want to consider. And that's where stemming that we mentioned in passing might be useful. So looking for a stem match for the last part, usually a fairly good compromise. It might give you a few false positives, but also it would reduce the amount of why isn't my document among the search results. There's also some libraries available. The Snowball project provides implementations for a few languages. It's not that difficult to write your own. The Python snippet over there was a bad implementation using arrays and so forth, but it's not that difficult if you look into it. There's also something called lemmatization, much more difficult, usually applicable to phrases rather than individual words. But on iOS, for example, there's an NS linguistic tagger that does this for you. So you might want to take a look at that as well. So as a final remark, reminder, it's not necessarily the technical correctness or the algorithm that matters. It's what the user expects to see when they type in those words. So the better you're able to serve what the user expects, even if it's something funny or sort of unoptimal, that's probably how you win this game. So that's all. Thank you for listening. I'll be here for the rest of the day, and you can reach me online or email, Twitter, over these handles. Thank you.
Thank you very much.